Hello and welcome to today's video. Up to this point, we've discussed a lot of different topics in calculus. Notably, we've spent some time discussing differentiability and applications of differentiability. Now, starting in this video, we'll talk about the reverse of differentiability, which is integration. The connection will only become clear later. For now, the goal of integration is basically to compute the area below a function graph. So to be more precise, the area below the x-axis and the function graph, including the sign. So we want to determine this area. And of course, the question is, how do we do this? And what does that lead to? So this first section is called integration of step functions. We'll define the term step functions in just a minute. The idea is to first restrict ourselves to a set of functions where we can easily define an integral, and then see how we can generalize that idea to more or less arbitrary functions. So we'll start this, as I said, with the integration of step functions. Once again, our goal in this and the next videos will be to determine the area between a function graph and the x-axis. Let's have a look at a quick example to demonstrate what exactly we mean by that. Let's say here's a coordinate system. Let's say we have a graph in that coordinate system that looks like this. And we're interested in the interval that starts here at that point and that ends here at that point. So that's the interval that we want. And now we want to determine the area of that function graph in that interval. And more specifically, what we do is we determine a signed area or a sum of signed areas. So the area above the x-axis, like this area, for example, that will be counted positive, and that will also be counted positive here. So that's counted with a plus sign. Whereas areas below the function, below the x-axis, like here, will be counted negatively with a minus sign. So for the integral, we'd like to have the sum of signed areas of a graph in the interval that we integrate over. Now, as I said, going right at arbitrary functions is a little hard to do. So our intermediate goal is to find a class of functions where defining that integral is easy. So we'll start with that. Let's say this is the intermediate goal. We want to find a class of functions for which that goal is easy to attain. So for which this area can easily be determined. And we'll first define an integral on that class. And well, when it is easy to determine an area, is of course the case for functions that lead to, let's say, easy geometric shapes for that area. And probably the easiest thing you could think of are rectangles here, geometrically speaking. And that leads to the notion of step functions. So basically, a step function is a function that looks like the following. Let's have a graph here. So a step function is a function that is constant on intervals. So basically what we have is a function that looks like this, for example, here, constant value in that interval, then maybe a different constant value on this interval, another constant value on that interval, and of course the length of the intervals may be different. And then we have another constant here. And then it's of course not hard to determine the corresponding areas, because what we have here are basically just rectangles, right? So this is a rectangular area. This here is a rectangular area. This is a rectangular area. And of course we also have that negative area here. So the one below the axis, this is also a rectangular area. So basically that area is determined by the length of the respective interval, by the function value, which gives us the height here, and of course by the fact whether it's above or below the x-axis for the sine. So this boils down to areas of rectangles, and you will also notice that the function values at these points where we change from one rectangle to another are not relevant for this rectangle area. So in particular, we can define that function value here, for example, like this, or also like this. So even if the jump is not onto one of those two rectangles, it doesn't really matter. It doesn't make a difference for the area, because that here will lead to a rectangle with an interval length. So one side here has the length 0, and that of course means the area is 0. So that does not make a difference. So the function value on these jumps is totally arbitrary. So we might define it like this, for example. Okay, so the point is, in these step functions, the areas we get are rectangles. So we have areas of rectangles, and those are easy to compute by simply saying what we need to do is we need to take the interval length, and we need to multiply this interval length by the function value. And then we just need to sum up over intervals. So all we need to know about our step function is this subdivision here into suitable intervals that correspond to the function value so that we get the right rectangles. Let us try to define this more precisely. Here's the precise definition. In integration, we'll usually work with functions that are defined over an interval, more precisely bounded functions, at least for now. So we usually assume we have an interval. It doesn't really matter whether it's open or closed, because as I just argued, the function values on the boundaries do not really matter here. As long as the function itself is bounded, we'll usually assume a bounded interval, unless we have reason not to. So in this case, we want an interval of the form a, b. We call that interval I, and that's an interval that is a subset of the real numbers. So let that be an interval in R. And then we define the following notions. First, we'll define what we'll call a subdivision of that interval. Basically, that means what we do is we put points in that interval at the right values. So for example, here we'll start our interval at this point, we'll end our interval at this point here. So those are going to be the end points of our subdivision. And then we need to know where each rectangle starts and ends. So what we like to have is we like to have these points here, and a collection of points in that interval will simply be called a subdivision. And for a step function, we always need a corresponding subdivision to be able to compute the correct rectangles here. One thing to mention is, of course, this is not the only possible subdivision here. We could also refine that. For example, we could put one more point in here, or in here, or maybe 2 points or 3 points in here. That does not really make a difference for the result. We will get more rectangles, so we divide those larger rectangles into smaller ones, but again, the sum of areas will be the same here. So we stick to a general definition of a subdivision first, and then define step functions based on that. Okay, so a subdivision of the interval I is simply a set of points. We'll usually label these points x0, x1, and so on up to some xn, such that, and the only requirement will be the leftmost point is going to be x0, and that's equal to the left bound of our interval. Then the other points are ordered in increasing order, so x1 is strictly less than x2, is strictly less than x2, and so on, up to xn, which is equal to the right endpoint of the interval, b. So for our interval, say here's the interval from a to b, here's a, which is equal to x0, here's b, which is equal to xn, let's say x3 for example, and then we have 2 more points, x1 and x2, which are more or less arbitrary points in that interval, with the only requirement being that they are ordered and not equal to the endpoints. Yeah, so they all need to be different. That's what we call a subdivision. And of course, once we have a subdivision like that, it's easy to define a step function. A step function corresponds to such a subdivision and assumes constant values on each interval given by that subdivision. So let's define that. A function, we call that function S, defined on that interval I with values in R, is called a step function on I if there exists a subdivision x0, x1 to xn for some n of I. And this is called the corresponding subdivision. With the following property, such that S is constant on the intervals xk minus 1 to xk, so between xk minus 1 and the next one for k and n, so from 1 to n. So as an example, we have a look at this subdivision that we have just seen. A step function on that subdivision, for example, would be the function that is constant here between x0 and x1, then constant between x1 and x2, and then again constant on x2 to b. We do not say anything about the function values that are on the interval boundaries. So for x1, for example, the value may be here. For x0, it may be here. For x2, it may be here. For b, it may be here. That don't really matter, as long as it's constant on the interior of that interval, on the open interval. So that's a possible step function corresponding to the subdivision of y that we have seen before. And we introduce a notation for the set of all step functions that will simply be denoted by S of I, capital S of I. So the set of all step functions on I will be denoted by S script S of I. And of course, for each step function, there is such a corresponding division. So the division is not given, it's just the interval that is given here for this S of I. And finally, we're ready to define an integral over step functions. And again, that's not going to be hard to define. What we do is we just take the step function, we take the corresponding subdivision, and we just define the integral as the sum of areas of the corresponding rectangles. So point 3 of our definition is the integral here. So let's say S is a step function defined on I. Let S be a step function with corresponding subdivision x0, x1, and so on up to xn of I, meaning S is constant on each interval xk minus 1 to xk for k in n. And furthermore, we'll also introduce a notation for the function value. Furthermore, let gamma k in R be the function value of S on the interval xk minus 1 to xk for k in 1 to n. And then we can easily define an integral. So the integral of S over I, and we'll denote that as either the integral like this here of S over I, so we put the I below the integral in the subscript, and we write that as S of x dx. So this dx denotes the integration variable. In this case, that's x. The choice is pretty arbitrary. We can also use the notation where this interval is made explicit. So we have the bounds a and b. And we can just write a as the lower bound, b as the upper bound on the integral sign. So this is the usual notation for the integral. And in this case, for step functions, this integral is defined as, well, the integral of S of x dx from a to b is simply the sum of the gamma k, the function values, times the length of the intervals, and that length is xk minus 1. Notice that we know that xk is strictly larger than xk minus 1, so this expression here is always positive. And we sum from k equals 1 to k equals n. So that is the integral. And in our example here, with this step function, the integral that we get will then simply be the area of these corresponding rectangles here. So this will be counted positively. This will be counted positively. And this area below here, that will be counted negatively. Yeah, the function value is negative, so that enters here in the negative. That means if you really want the area, then of course you'll have to use the integral over the absolute value of that function s. Yeah, with the usual integral, what you get is the signed area, or the sum of signed areas. Quick example. Let's say we have the following step function. We have s defined on the interval 0, 6 to r. And let's say s of x is defined in the following way. It will take on the function values 3, minus 2, and 1. It will be 3 for x between 0 and 2, and let's say we include both bounds here. It will be minus 1 for x in 2 to 5, 5 included, 5x, 2 excluded, and it will be 1 for the rest, so x in 5 excluded to 6 included. And now, of course, we can choose a corresponding subdivision. That's easy in this case. So a good corresponding subdivision will simply capture all those jumps. We have to start, of course, at 0, the left bound of the interval. And we can choose x1 to be 2, because that is going to be the first change here. x2 will then be 5, because 5 is the next change, and 6 here is our right bound of the interval, so we need another point in our subdivision, that is x3, which is 6. So how does that look like? Let's have a quick look at a sketch here. So let's see, 1, 2, 3, 4, 5, 6. So we want minus 2, minus 1, 0, 1, 2, 3. That is the value axis. And then we need an x-axis. And it's at least 6 long. So 1, 2, 3, 4, 5, 6. This is our interval here. The subdivision that we chose is 0. That is x1. x0, sorry. Then 2 is the next point. That is going to be x1. The next point is 5, x2. And finally, we have x3 here at 6. So that's our subdivision. And the function itself takes on the value 3 in the first interval from 0 to 2. So here we get a value of 3. Boundaries included. Then we get a value of minus 2 in the interval from 2 to 5. So what's this here? First boundary excluded, second one is included. And finally, we get a value of 1 for the interval from 5 to 6. So this is this interval here. And here the right bound is included, like this. Okay, so this is the step function. This is our function s, or the function graph of s. And now the integral can simply be computed by looking at those intervals here, and then at the corresponding rectangles. So we have this rectangle here that will be counted positively. The area of that rectangle is, well, the function value is 3. The length of that interval here is 2. So that means what we get here is 2 times 3. That's an area of 6. And just to denote that as well, gamma 1 is then the function value here. That's 3. Right? That enters here. The next is negative. So this rectangle down here will count negatively. So what we have here is a function value gamma 2 of -2, and that means the corresponding a value of the area here, the value that enters the integral, is going to be 3 times -2. So that's the -2 is this one here, and the 3 comes from the interval length, that is the length of 3 here. And finally, the last interval has a length of 1, and again the function value is now positive. So we have this rectangle here. The function value is now gamma 3 equals 1. So what we have here is an area of 1 times 1, which is 1. Right? And again, the gamma 3 enters here. And I forgot to give you the result here. So 3 times -2 is, of course, -6. So what do we get as integrals? Well, of course, that depends on the interval that we use. Of course, if we integrate like from 0 to 2, that's only the first rectangle here, this one, s of x dx, then what we will get is 6, the area of that rectangle here. If we integrate from 2 to 5, that is the red rectangle here, then we get this area, -6. If we integrate from 5 to 6, then what we get is this rectangle here, so the area of that is 1. And of course, if we put it all together and integrate like from 0 to 6, s of x dx, and that's just the sum of all these rectangular areas, so we get 6 minus 6 plus 1, and that is 1. And of course, we can also use integration on sub-intervals. For example, if we integrate from 1 to 4, let's say, we have 1 to 4, this part here, so we get part of that rectangle, half of that to be precise, and we get part of that rectangle, 2/3 of it to be precise. That would mean we get 1 times 3, that's the function value on the green rectangle, plus we get 2 times -2. -2 is the function value on the red rectangle, and here we have an interval length of 2, and here we have an interval length of 1. So we end up with 3 minus 4, that's -1. So just as an example, that's how these calculations work. And of course, if we're actually interested in the area, we could also compute the integral over the absolute value of s of x dx, and that would then be 6 plus 6 plus 1. So here we get 13. So if you want the area, that's 13 in this case. Okay, so this is how you define integrals on step functions. Let's collect a few properties of the integral on step functions before we move on to arbitrary or more or less arbitrary functions. So that's the first theorem about integration here. Oops. And you'll see that works pretty much the same for arbitrary functions. That's why I'm listing this already. So, as usual, let I be an interval. We'll again take a closed interval, but we don't need to have that closed in our interval. And we want a step function s defined on that interval. On I. Then the following are true. First, of course, the integral does not depend on the choice of subdivision of I. So the integral s of x dx over I is independent of the choice of corresponding subdivision of I. So if you look at our example here, for example, we could as well have chosen to add points to those subdivisions. So we could have added a subdivision point here, or maybe one here. It would not make a difference. It would give us a little more sums, but the rectangles would have the same height. So again, the difference would be none, basically, for the result. It just makes the computations a little more complicated. But the important point is the definition does not depend on the choice of subdivision, of course. Second part of our theorem, any constant function on the interval is, of course, also a step function. So we can also integrate constant functions. Any constant function on I is also a step function. Third point, that may be something more interesting now. If we have two step functions and consider a linear combination of those two, then we can integrate that linear combination because that is also going to be a step function. So if S1, S2 are step functions on I, and lambda 1, lambda 2 are constants, real numbers, then lambda 1 S1 plus lambda 2 S2 is again in S of I. Or in other words, what you can say is that for any two elements, any linear combination of those two will also be contained in Si. So that means Si with the usual pointwise addition and scalar multiplication of functions is a vector space. So in other words, Si is a vector space. And of course, for a vector space, it's interesting to see how the integration behaves as a mapping. You can think of the integral as a map that takes a function and outputs a real number. And as it turns out, this function is actually linear. So more precisely, for S1, S2 in Si, so two step functions, and lambda 1, lambda 2 in R, we have the integral of lambda 1 S1 of x plus lambda 2 S2 of x dx is equal to the integral of S1 of x dx times lambda 1 plus the integral of S2 of x dx times lambda 2, both integrals taken over I. In other words, the integral is a linear operator. The integral is a linear mapping that takes a function, a step function as an input, and outputs a real number. And functions that take a function as an input and output a real number are often called functionals. So in other words, this is called a linear functional. Yeah, so functional is a mapping that transforms a mapping into a real number, a linear functional. And finally, an inequality that is often valuable. So again, if we have S1, S2 in S of I. And if one of those is less or equal to the other, so if S1 of x is less or equal to S2 of x for all x in I, then this is also true for the integral. So that means the integral of S1 x dx over I is less or equal to that of S2 of x dx over I. In particular, that also means the integral of a step function, s of x dx over I, is always less or equal to the integral over the absolute value of s of x dx, because s of x is less or equal to its absolute value, so this again also holds for the integrals. And again, that is going to be a theorem that also holds for arbitrary integrals, basically just by extension of that fact from step functions to arbitrary integrals. And how that extension can be performed, how we will be able to integrate more or less arbitrary functions, that will be the central topic of one of the upcoming videos. And as always, I'll be happy to see you then.